Hello, my name is Giancarlos Fuentes. I'll be presenting the first part of my group's research project. We decided to do AI deployment in low-power IoT systems, specifically using the MAX78000. First, we have an introduction to what is embedded AI. Embedded AI refers to AI models that run directly on IoT devices as opposed to relying on cloud processing. This is crucial because it reduces latency, power consumption, and security risk. A great example of this is the MAX78000, which is an AI microcontroller that enables real-time AI processing on low-power devices. The article we reviewed highlighted a shift from cloud-based AI to edge-based AI, where computation takes place locally. In traditional AI processing, data is processed in the cloud, which takes up a lot of power, causes delays, and causes potential security risk. However, embedded AI solutions have helped by running directly on devices like the MAX78000, which allows for faster, more real-time processing at lower energy costs. Therefore, AI is vital for battery-operated IoT systems like wearable devices, remote sensors, etc. Here you could see an image of the MAX78000 AI microcontroller. And next, before we dive into the controller itself, we have to talk about challenges of AI within IoT. Because of their nature, IoT devices typically run on small batteries, but as we know, AI models do need a lot of energy. Also, AI could cause latency issues between sending data to the cloud. It could slow down real-time applications, and also transmitting sensitive data also increases cybersecurity risks. Within the introduction section of the article that we analyzed, we realized there was an emphasis on the idea that cloud-based AI solutions aren't practical for small, lower-power devices. Hence, since IoT devices usually have limited energy resources, running AI smoothly is a major challenge that we face. However, many AI applications like smart surveillance require instant processing as well. Therefore, latency is also another challenge that we face. And privacy and security also pose a threat when transmitting IoT data to cloud servers, where sensitive information could be exposed to hackers and/or data breaches. So, as a summary of challenges of AI, we realize that there needs to be an on-device AI resolution within IoT applications that, one, minimizes power use while still guaranteeing real-time performance. This is a figure directly from the paper we researched, and this quote from the paper states, "Figure 1 illustrates the performance and power trade-offs among various AI accelerators, showcasing the diversity of solutions available for IoT applications." As you could see, these are some of the most popular and quote-unquote strongest AI accelerators. They're very high in performance, but also take up a lot of power, which wouldn't be practical, like I said, for IoT applications. However, these in this little blue circle, you see the MAX78000, GAP9, and GAP8, which are some examples of AI accelerators that, still give you a good performance without using a lot of power, which is what we're looking for in AI and IoT applications. Next, finally, we could introduce the MAX78000 itself. The MAX78000 is an AI-powered microcontroller that is designed for low-power AI applications. The board features a built-in CNN accelerator for efficient neural network interface. The microcontroller also runs on milliwatts instead of high-power AI chips, which leads to ultra-low, super minimal power consumption. And most importantly, some could argue, the MAX78000 is designed for IoT applications as it works in wearables, smart sensors, and industrial automation. Whereas your normal AI processor may require cloud connectivity or a strong GPU, the MAX78000 on the other hand executes neural networks within the device, like I previously stated, and the CNN accelerator also uses very little energy while running certain AI tasks like computer vision models, keyword spotting, etc. For example, just a little comparison with other high-power AI chips. The NVIDIA A100 is a powerful AI chip, but consumes too much energy, where it wouldn't be practical to be used within IoT applications. Other hardware, like edge AI devices, such as Google Coral, utilizes a moderate amount of energy and are suitable for some IoT applications. However, what we're looking for, like the MAX78000, it's designed specifically for ultra-low power AI processing, therefore it's ideal to be used in IoT devices. Once again, this figure is taken straight from the article. It shows the architecture of the MAX78000, the microcontroller. Here you can see the memory, the CNN accelerator. It features an ARM Cortex. The external interfaces it allows for. Basically, this microcontroller is built around IoT. Therefore, we think it would be extremely suitable to be used in these scenarios. Thank you, and I'll leave you with the rest of my team.
Hi, I am Brandon Gerbers. I'll be carrying on with the presentation on the MAX78000 embedded AI controller. I'll first be talking about how does a neural network work. A neural network are designed to mimic the human brain with layers of artificial neurons that process and extract features from input data. The key components of a neural network are the input layer that takes raw data, images, sensor readings. The hidden layer processes, extracts features using mathematical operations. Output layer provides final predictions or classifications. An example of this done, as you can see on the right of the presentation, you can see a roadmap sign recognition. The input layer receives an image of a roadmap sign. A hidden layer detects edges, shapes, and patterns within each neuron of the stops or of the roadmap sign. And then the output layer classifies the image as stop or yield. Why a CNN accelerator is needed. So in standard microcontrollers, MCUs struggle with deep learning tasks. This is due to limited processing power. AI models require thousands of operations per second. Memory constraints. AI models can be large. Energy consumption concerns. AI tasks drain battery life. How the MAX78000 handles these operations. The MAX78000 CNN accelerator handles AI computations efficiently by doing the following. It has a dedicated AI processor and RAM storage for weights. The weights store trained data model parameters, and then pipeline operations. This allows it to run multiple AI tasks in parallel. How the CNN processor works on the MAX78000. It reads input data from sensors, images, or audio signals, processors, AI layers in the CNN accelerator. Computations, a mathematical operation is performed. Pooling reduces the data size while preserving key features. Activation functions introduce nonlinear for complex learning. Generates output results. This classifies an object or detects a keyword. Where in a MAX78000 can be used? It can be used in voice assistance, low power AI voice recognition, keyword spotting, and simple speech recognition tasks on AI devices. Think of smart home applications, lights, thermostats, locks that you can wake up with a keyword or a simple voice command. The chip's low power listening capability means devices can remain always ready for a trigger word without draining the battery. A smart camera. The MAX78000 can be used in smart camera applications such as an AI-powered image processing, This can be used to power smart cameras for image sensors or perform object detection or classification on devices. Industrial IoT sensors, real-time anomalies, uh, so detecting industrial settings. The MAX78000 could be embedded in predictive maintenance sensors, devices that listen to machine vibrations or motor sounds and use AI to predict failures or maintenance needs. The chip is well suited for analyzing vibrations or other signals for anomalies. Also, its low power draw allows it to be used in remote signals or sensors, such as running on battery or energy harvesting. Medical wearables, monitoring patients' vitals, wearable IoT devices like fitness bands or health monitors can leverage embedded AI to interpret sensor data in real time. The MAX78000 can also run algorithms on accelerometers or ECG data to detect patterns, for instance, identifying heart signal concerns, counting steps, or classifying activities, running, sleeping, or detecting falls in the elderly.
All right. Hi, this is William Coleman, and I am presenting the part three of um, embedded AI for IoT devices. And I am going to be trying to convey, not in too much detail. The paper was pretty big, and me personally, I didn't get to read all of it. I had to skip over and focus on these sections. So let's start. I'm developing AI models for Max 78,000. This is the IoT device that was being chosen by the research paper. I also happen to actually have one. This is the FTA, the Max 78,000 FTHR. I'm using it for a competition. But besides that, we can get into this. AI models for Max 78,000, it must be compact, efficient, and optimized for edge devices, such as the Max 78,000 or, other IoT devices. And the networks need to be defined. Uh, the models that are going to be used for it, and they need to, they require defining a network architecture. And, you can use the Y HTML files are what's going to hold the hardware defining features or, descriptors. It's going to describe layers, activation functions, and resource allocation. And with the training pipeline, you're going to use tools like a PyTorch to build and train models. And you can generate, checkpoint files containing trained weights and architecture details. The network must be adapted to specifically fit, for the case of this paper, Max 78,000 constraints. And, if you use different device, then it'd be different constraints. Training AI models, gradient descent and optimization. The training process finds network parameters through forward inference and back propagation. Forward inference is like, testing over and over again. Back propagation is getting those results, seeing what these, the little issues, and then doing tweaks, and then keep going back and forth and back and forth and back and forth until you get some really good desired results. Requires a well-configured learning rate schedule, or tuning to improve model performance. And hardware acceleration, the GPUs, the special hardware, and they tend to accelerate the computations that occur on the board, or just what you have it set up with. The Max 78,000 that supports quantization aware training, or QAT, for optimized inference and efficiency. And the monitoring process with TensorBoard, you can use it to logs, or logs track performance metrics, or logs and tracks performance metrics like loss, accuracy, and confusion matrices. This is the example of a loss, graph, and this example of the box, where Or I mean, here it's talking about epochs, and you have loss here. Epochs are like the different iterations of training, and you can see the more you do them, the less loss you have. And here you can see the accuracy here, where you see this line, but as you do more and more iterations of it, it gets more precise. And well, the deploying models on this MAX78000, you're going to need to do a lot of conversion. This AI8 XIZ, it's like synthesis, and it comes out to this Python file, this script, and it's used to generate C code from the trained models. And again, the YAML files, they have the hardware specific configurations. Well, the actual steps are converting trained models to quantized format, generating the CNN inference code, which I think my partner would have already explained what CNN is, because I just like the blinking right now. But I know it's a neural network, but I can't remember what C stands for. You're going to compile and flash a model into the MAX78000 and then run real world inference and validate the performance. Make sure that you get to get results. And some challenges, considerations to think of are when you're optimizing for the 78,000. A little bit more detail is that memory constraints. The models must fit within the 512 kilobytes of RAM that's on the device, and of the 442 kilobytes of like weight storage. And well, efficient quantization. Reducing precision, save space, but it may lower accuracy, and then consistent pre-processing. You're going to make sure that input data is the same during training and the inference when you're testing afterwards. I know example inputs are like audio features and image scaling. And well, that should be it, honestly. Thank you.